this side of campus. Just
Really?
From Arthur.
Oh, you mean from all of the
From all the
vehicles?
cars running down Arthur on the west side of campus, because I live on the east side of campus over south of there, and
Right.
I ride my bike up to Arthur, and just in that 5 blocks, you
Yeah.
can smell the difference.
Wow.
Yeah, I hold my breath a lot when I'm biking.
Like
Seriously, it's the only way. Or there's like dust coming out my face. Or something.
oxygen
I do that
deprivation
when I
training.
start smoking.
What was that?
Said I do that when I walk by someone that's smoking.
Yeah, happens a lot.
Yeah. I just realized that I did not record any of this, but it's okay. I think everybody's in class. The only person that's not here is Daniel today,
Well,
but
that's good.
that's all right. Yeah. No, this is one of my favorite things, and it was something I didn't really pay much attention to until I so I was actually teaching it. I was like, oh, I got to learn it. Well, start teaching it, kind of becomes fun and cool, and and very relevant to to the geothermal we're talking about.
It's a shame I missed the first part, but I'm getting the gist of it.
Yeah, it's just, and it goes back to that simulation. This is kind of the 1D version, just showing that the
Show them the melty one.
the melty. Yeah, let's look at that one.
That
Okay.
was cooler.
A little clearer demonstration.
Yeah, it makes.
Oh, there it is. Yeah.
Yeah, it brings back the summary we did on radiative forcing as well.
It does a little bit. Sure. Yeah, it does. So there's that. There's this guy, and then we showed that the Earth radiates at 60 milliwatts per square meter. And then so I'm glad you asked that question though, Mariah, because the thermal battery, this would be a low enthalpy operation where everything here in Australia is high enthalpy.
And that the 100C is just,
What's that?
the 100C is the cutoff for that.
100C is the basic cutoff because it's probably a little higher than that, but that's where water boils.
Right.
100C.
The other thing is that then you have a lot of water storage, which isn't a bad idea.
Sure.
That's a, like emergency
Yep.
preparedness.
Yep. Water storage too. Absolutely. This guy is pretty cool too. And I guess I'll just take one more moment to show you some cool mechanics that I love thinking about. If we have a chunk of material, there we can do this to it. We can push on it with a force in the x direction. We can push on it with a force in the y direction, and we can push on it with a force in the z direction. These are the three normal forces. So there's a eraser in here. This is the easiest thing to do, is just to show that I've got a eraser. So I can push on it in x, I can push on it in y, I can push on it in z. Those are all three normal forces, which are vectors. But I can also push on it here. I can push on the x face in the y direction. So this is f, x, y. I can push on it in the y face in the x direction, so f, y, x. And so this might be kind of hard, but I'm sort of pinching this eraser now just on the corner. If I did it just right, I could hold it without actually applying any normal forces, kind of like gripping a basketball. Like when you grip a basketball, there's no vacuum in your hand to hold it up, and I don't know, maybe if you have really, really big hands, you can reach halfway around the basketball to hold it, but that basketball is being held with these friction forces, right? So you can also imagine doing the same thing. Now I'm on the x direction, so this is f, x, z, z, and this is f, y, z. So now I've got three types of forces, because remember there's three spatial dimensions, at least that's convention. You could also say this is f, z, x, and this is f, z, y. And so that's basically all the forces you need to hold something in place. So this is static mechanics. What we're seeing here is fracture mechanics. So I think someone mentioned last time, maybe Rob said, well, as the moon goes around the Earth, as the Earth goes around the sun, there are gravitational forces pulling, and what we're seeing here is something that's slipping. Well, what happens when it slips? Well, you just got to rub your hands together. It gets hotter. That mechanical energy turns into thermal energy, and that's really all that's being shown here. So, and the other fancy name for these guys. So these are all normal. What you can do, and this is also another one of my favorite parts of mechanics, is you can put these into a tensor, and it actually ends up looking like this. It's sigma xx, sigma yy, sigma zz, sigma xy, sigma xz, sigma yz, sigma yx, sigma zx, sigma yz. Why did I write sigma? That's just the lowercase Greek. Why did I write sigma instead of F? Well, it's stress. It's not force anymore. Because stress equals force per unit area. The other really cool thing about stress, not bad stress, not stress over your final exams, but stress is that if I multiply force and area both by distance, I get energy per volume. So when we were doing waves a little bit ago, we talked about internal energy. Stress is also internal energy. We also talked a little bit about how expensive it is to drill. Well, it's stress that breaks the drill. It's energy per unit volume. That material simply cannot hold any more energy per unit volume, and it breaks. The external energy overcomes the internal energy, and it fractures. So that's what's going on there. Is that your favorite?
I've never seen another one.
What's the worst part of that?
Going out to the shaker to collect a sample, get diesel on them.
Oh, really? Okay. Sounds fun.
Oh, yeah.
What's going on in these guys right here?
That's the doghouse, so the guys who actually operate the machinery.
Sort of like attaching, detaching, yeah.
Precisely, yeah.
Okay.
And all the mechanical instruments and the directional drilling goes on in there.
Yeah.
But yeah, back behind it, all of the rock fragments that are coming up from the drilling process,
Yeah.
brought up by the mud.
Yeah.
And as a geologist, you got to go dig through the mud and get a sample every 30 feet.
Okay.
So if they're drilling at 120 feet an hour, your life really sucks.
Mm-hmm.
I hated it.
I'm guessing it's kind of smelly too, right?
It's awful.
Yeah.
It'd be 3 or 4 days after I left the rig when my hands finally stopped smelling.
Oh, yeah. I'm watching these directional drillers now. I think they're putting in new, Cat 6, Cat 7 or what up in the rattlesnake.
Mm-hmm.
And is a lot of fluid being pumped down here too? 'Cause I notice when these guys go to do their they'll first flood it, and it's just that much easier to get the soils and the rocks all. Is the same thing going on?
Oh, yeah.
Yeah. Okay.
And they bring in all that tank down there to the left, like,
This guy?
yeah, that right there.
Yeah.
That's a water tank.
Yep.
They use that to mix the mud
Right.
and then send the mud down the
They
hole.
just put windows up in the rattlesnake?
Well, no, in the rattlesnake, so pick your poison. Do you want to see a bunch of lines, overhead, or do you want them underground? Well, in general, it's more attractive and to a large extent safer to have your power and your signal underground. So you can either cut up the street, cut up the sidewalk and lay in the hole, or you can drill under the street and the sidewalk. So these, what are they called? Vermeers?
Yeah.
The Vermeers? Yeah, so here's another example. They're actually pretty cool. You look at them, man, that is some cool Vermeer trencher.
I like that, all this information on where, like, all these fiber optic cables and pipelines and all this stuff underground. Like, I really hope that information's easy to get a hold of.
Yeah.
Or it's passed down properly to the right people as time goes on?
Yeah.
Because
It's not the trencher, though, it's the driller.
That's
Just
what I
say a
need to hear that
directional
damn
drill.
breather, man. Great.
Giant chainsaw.
Yeah, it's these guys.
Yeah.
I mean, they're big, they're heavy, but, you know, and as you go further, under the neighbor's yard, and the coolest thing about them is there's like a little shoe, and so there's the drill head's here, and there's a shoe, and as you change the direction of the shoe, I think that's your directional drilling, because it kind of acts like a little cup or a plate to steer it, so.
It's neat they can do it on such a small scale.
Yeah. What were you going to say about, you hope that what now?
About how I just hope that all the information on where all these fiber optic cables and pipelines and all this underground crap
Is,
I just hope
right.
the information is easy to get a hold of.
Right,
and passed
yeah.
down to the right people.
Likewise.
as things change, because I highly doubt people are gonna be really concerned about that, when they.
Well, we had to do the same thing when the new Missoula College building went in. We had our wind turbine over there, and there was 200-foot, double-aught copper underground, and they were about to, start digging. They didn't want to have to, when you pull a tree root and you're digging your backyard and here comes a tree root, well, they didn't have to, have the whole sub-panel pulled off a block away. So,
Yeah.
Yeah,
you
you
do
gotta
it.
be careful digging.
Yeah,
A colleague of mine, when I was doing the sinkhole investigation, died.
Yeah.
Because the electrician didn't properly mark the orange lines in the yard.
yeah,
And he just had a little hand auger
yeah.
down like 2.5 feet right into the line.
Oh, and it electrocuted him, or, that's terrible.
Yeah, it
Yeah,
was-
see, stuff like that.
Yeah. One more reason to go off grid. Just, yeah. All right, what else we got here? Power output. Okay, here's your question then, Tyler, on your costs. So let's see, long-term marginal cost. This is New Zealand dollars. New Zealand dollars per megawatt hour. So this is, this is power. So we're looking at, this is a gigawatt plant, right? So coal strip would be out here. This is basically a half a coal strip. I guess what's a little surprising is that the bigger ones, I would actually expect this to sort of go down as they got larger. That's what's a little bit, wait, here we go. This is power output, and this is per megawatt hour. Per megawatt hour.
Generate at different rates.
Well, let's think about that guy. It might just be the lifespan. Why is lignite so? I'll have to look at that. I'm not exactly sure why those curves go that way. Because you would think that over the long run, the energy cost would go down. It could be though. It could be though that as the plant ages, it gets more expensive. Yeah, that could be what it is.
And they might even have to drill deeper over time as well.
Yeah, it could just be that your energy becomes more expensive as your infrastructure decays. That's my interpretation of that one.
What's the lifespan of a geothermal plant?
Well, again, the lifespan is going to be dependent on, so, obviously the materials there will fade. If you draw from it slowly, it could be as long as you like, really. If you draw from it too quickly, though.
No, I imagine
Yeah.
there's a middle, a Goldilocks zone
Yep.
where the recharge is approximate to what you're taking out.
Mm-hmm.
It's probably wishful thinking.
Well, yeah.
All right, well,
yeah.
that doesn't make sense.
Yeah. Something to keep you awake at night. All right. Percentage of electricity demand, and we mentioned Iceland earlier. Lots of high enthalpy. There's New Zealand. New Zealand's right there, doing pretty good shape. And these are the leaders. This is kind of weird. You're like, well, why wouldn't the world be more? Well, it's just the percentage.
It's funny, a place called Iceland.
So then,
Yeah.
geothermal energy is sort of like more accessible to places that are more like volcanic.
Yeah, oh, yeah, absolutely. Yep.
So there's a lot of places that there could be a potential.
Yeah.
Yep.
I came across a
Yep.
statistic during
Hawaii. Yep.
one of the first summaries that we did, one or two, that Indonesia has 40% of the world's potential geothermal energy.
Really.
That's what I read.
Okay.
Because I investigated, because I was like, 40%, that's impossible.
Yeah, well, another thing that's surprising, or maybe not so surprising, Tim Chester used to talk about this, is what fraction of the Earth population lives near volcanoes?
Yeah, the Ring of Fire.
Yeah, Ring of Fire or whatever, so, yeah, New Guinea, there's another example, hanging out there.
Well, yeah, Indonesia's got a population the size of the United States, small island nation, but everything's a volcano.
Right. There we are, and these numbers will only increase. Now back to jolly old England, and so here they're talking about specific geological structures. So Mesozoic basins, radiothermal granite batholiths. There's actually maybe a little bit of radioactivity going on there. This Lamy Basin. So different well sites. If we look closely, we can see the Marchwood, Southampton, Larney. Here's the Cleothorpes out here on the edge. So a little bit of geothermal prospecting going on in the UK as well.
England really doesn't like Ireland, do they?
That's what I've heard. That's what I've heard. Heat pumps unit per year. I don't have my text with me, so I don't know exactly why that peak occurred. But obviously on the rise. Here we are in 2017. Who knows what happened after that? They're just looking at different temperature gradients. So think of a sort of an underground weather map, if you will. That's it. That's pretty much it for chapter 9. Anything else you guys want to talk about? I've got one other thing I just want to show you. One other thing. So I was walking over here, and there's a lot of stuff going on in the news lately about economics, Bitcoin, different currencies being created. And one thing that I am working on right now, actually I'm going to show you two things. Maybe I showed you this paper, but I just want to remind you where the thought came from. So if we go back to papers, 2016, there's this thing I published last year. Here's the online version. And I just wanted to remind you of this whole entropy thing, because what ends up happening, and I even have an example way down here. Actually, it's not in this paper, it's in the other paper. One quick second. VLA documents, courses, conferences, 2014. This was the precursor to the 2016 paper. So we kicked off this lecture talking about the Earth radiating into space, right? And there's this problem. Oh shoot, let me find it. Maybe it was in the other paper. Yeah, I think it's in this guy. Let me just find it. Oh, here it is. Yeah. Entropy generation rate of a pair of planets. So we talked about the Earth radiating into space at that 60 milliwatts per square meter. Talked about the sun's radiation coming at us at 1,000 watts per square meter. Well, if you had two planets equal size, so everything's radiating and everything else all the time, what's being shown here is that as heat transfer, so this Q dot is the rate at which heat leaves the planet. Temperature is the temperature of the planet. And you can see that both planets are about the same temperature. You know, it's about the temperature, that's about the temperature of another planet. But this guy is just a little bit colder. You can see that they're both radiating at the same rate. You know, the same amount of heat is coming off of both of them. And what ends up happening is that planet B is generating entropy just a little bit quicker. The heat's coming off just as fast, but it's colder. Now, when they interact, when you add both entropies together, the overall entropy goes up. So that's just a specific example of the second law of thermodynamics. It's saying that S dot, so remember the dot means how quickly something's changing with respect to time. So if we go all the way back to the notes.
So if it was a bigger engine, it would lose heat that faster. So
You can think of it as a bigger engine losing heat faster. Yep.
Planets conjoining.
Yeah. So delta T, delta temperature, delta T, is the same as T dot. That's exactly what that dot means. The dot just means how quickly something's changing with respect to time. So there it is. So this S dot is positive, and it's always positive. And that is the second law of thermodynamics. And so in this paper, so in this grant, and this is if I get hit by a bus this afternoon, at least I'll have it recorded on YouTube. Or if I go dig in my backyard and get fried by an underground line. It'll be on the inner tubes. Here's what I've been trying to kick around a little bit, is that here's the relationship among these things. So I think I showed you this. Did I show you this? You remember? Okay. So this is money. This is entropy. And this is information. So we know that the universe. And you could think of the ball as being time, and you can think of there like always being more time there was less time in the past, and now there's more time because we're moving into the future. You can think of the ball is just getting bigger all the time, expanding, right? Kind of easy. Where's time? Well, it's everywhere, and it's always perpendicular to everything else. So this is the second law sort of doing its thing, right? The second law is always getting bigger out here. In general, we humans and city planners and home cleaners and garbage collectors and et cetera, want to say, no, let's make it cleaner. Let's go back in time. Let's make it how it used to be. Let's make the world all neat and orderly. Let's push it here. Here's the fountain of youth is back here. Right? Well, sorry. This is the way the world goes. It's always becoming more disorderly. We just saw it on a planetary basis. Can't help it. Now, this stuff over here is information. And you can think of information as being like the very first scribble in the dirt, the papyrus, the Ten Commandments. You can also think of it as talking. you can think of what's happening right now where, I'm vibrating the microphone, it goes into the thing, it's going to sit out there on some server. So these are just,
Digitized.
these are bits. So yeah, so we're just, creating bits all the time. There it is on this axis. That's what I'm trying to show here is that its information is going up all the time.
And so by digitizing this information instead of recording on a tape, you're not increasing the physical entropy release.
Maybe not, unless the thing about Google destroying water is true. I don't know. We'll see. I don't know.
How?
Yeah, I don't know. Someone just said Google's destroying water yesterday. I don't know.
Their servers cool, I think.
They got to cool their servers, right?
Systems, yeah.
And they destroy it?
I don't know. I think they probably just make it really hot. I don't know.
Maybe they just want to claim that they're God.
Digitize the water.
Google is the new name for God.
Realities.
And this direction is you could think of this as misinformation. You could think of this as like someone telling a lie or a fib or alternative facts or book burning, what have you, right?
That happened a couple times.
That's the destruction of information.
Where?
It's digitally on the government EPA site.
I've seen bonfires.
Yeah. So I think we understand entropy somewhat. I think we understand information. And then this is money. And so humans have created money multiple times. There's hundreds of currencies, and we're making new ones all the time as well. So initially, there was no money, and then we said, well, we're gonna make some, and and I have some, and you don't, or somebody else has more. And then this is debt. That's financial debt. So in general, if you think about how much money there is, well, there isn't any money. We just made it up, and someone has it, someone else has debt. So what I'm trying to then construct is a system of equations where entropy sort of feeds back on itself. Information can feed back on itself, either in a positive or negative way, and money can also feed back on itself. Like that's your interest. This guy right here, I think, is the relationship. There's your Bitcoin right there, because your Bitcoin just sits as a set of ones and zeros somewhere on a server, and we treat it like money. So between these two guys are your Bitcoin. This is pollution. I'm sorry. This is pollution, so money going into pollution, and this is your cleanup. So your EPA is sort of over here on this branch, saying, here's some money, clean the place up, de-antropicize it. And then this over here is more or less your environmental monitoring. Hawaii, Mount Loa is there, measuring how much crud is in the air, et cetera, et cetera. So that's the little foundation that I'm kind of trying to build. And the point, if we kind of go back to Nash equilibrium, the point is like we'd like to be cleaner, richer, and smarter. And how do we how do we all become cleaner, richer, and smarter without stepping on someone else's cleanliness, wealth, and knowledge? So I'll just end with that. Yeah.
Did you come up with that diagram?
Yeah, I did.